Okay, good morning, good evening, good afternoon, wherever you are to everybody. I'm Amanda Valenta. I'm a senior energy specialist with the U.S. Agency for International Development, and I'm thrilled to welcome you all to our webinar today, Grid Modernization Actions to Improve Renewable Energy Integration. So we're here today because as prices for clean tech and storage continue to fall and nations look for new and innovative ways to curb their emissions, we know that integrating higher shares of variable renewable energy is increasingly critical and complex. So next slide, please, Christine. Today, through our program, through USAID's program Scaling Up Renewable Energy, we'll aim to discuss the types and sequencing of grid investments that are critical to managing for the flexibility that's needed for successful integration of variable renewable energies. So we'll look at key elements of grid modernization, and we're really going to focus in on the implementation components of this puzzle. One, because we covered a lot of those critical planning and policy and regulatory components in a previous webinar, and two, because we only have 1 hour. So we'll really be trying to tackle kind of the affordable bite-sized implementation pieces that are necessary to either start tackling or continue tackling grid modernization in the countries where you work. So we'll do this by mapping country level examples of grid modernization interventions in Kazakhstan, India, and Colombia, and then really taking some of the common components across those very different country contexts and presenting those so that ideally you'll leave today with a blueprint or a framework for grid modernization that you can apply to the countries where you work. We'll, of course, have some time toward the end of the webinar for Q&A and discussion. So just a couple of housekeeping items on that note. You can feel free to put your questions in the chat as we're going. All of our panel experts are here and can answer in real time, but we will have some dedicated time toward the end of the webinar for discussion. And at that point, we will just ask you to raise your virtual hand, come off mute, and we'll have a live discussion then. Next slide. We have a panel of experts here with us today. I'll just take a moment to properly introduce them. Ari Mataforte is our director at Tetra Tech and the chief of party for the SHORE program. She has experience in energy sector reform, strategic energy planning, and renewable energy projects, and also works across a host of MCC projects in Western Africa focused on electricity generation, distribution, transmission, as well as the development of electricity sector reform. We have PK Agarwal here. He's the former director at Power System Operation Corporation Limited in India and plays a key role in the development of India's power system from both the perspective of electricity market design as well as grid integration and modernization. So we're thrilled to have him here today. Tetra Tech's Alvaro Lopez Pina is an energy sector advisor and expert on energy transition strategy, policy, transactions, and green growth. And Victor Bedoya, who's an energy sector senior associate at Tetra Tech, has hands-on experience supporting energy sector reform, strategic energy planning, as well as climate change and the integration of variable renewable energy. Next slide. So I will just take a few minutes to set the stage for our experts to dive in a little bit deeper, starting with our grid flexibility. Next slide, please. So historically, grid flexibility, our ability to ramp power up and down in order to accommodate demand, has come from the supply side, from large power plants. But what we're here to talk about today is what we're moving toward, and moving forward, flexibility will come from the grid itself, more specifically to that modern grid. And this modernized grid ultimately makes variable renewable energy predictable, visible, and controllable. And that's really what we're aiming for and what we're here to talk about today. Next slide. So I know we talk about grid modernization typically for the reason of integrating variable renewable energy, which is obviously what I've harped on for the first couple of minutes already, but it's worth noting that there are several reasons to really focus in on this topic. Aside from integrating higher shares of renewables, we also have the management of these distributed energy resources that are already coming online in so many of the countries where we work. Electric vehicles, storage, all these types of things. And then accommodating new business models also requires a modernized grid. So things like the electricity access through mini grids, active consumers, vehicle to grid services, all of these are emerging business models that really require a modernized grid in order to function properly. And the one cannot function without the other. So it has to be a really combined conversation. And then finally, in the face of climate change, extreme weather events, providing secure, reliable, and resilient electricity is increasingly critical, and a modernized grid is a core component of that. Next slide, please. None of this is free. Of course, a modernized grid requires sustained investment. Right now, we know that the world invests about $300 billion US per year in grids, roughly 2/3 onto distribution and 1/3 onto transmission. But moving forward, we estimate, and we being our main forecasters from IEA, IRENA, and Bloomberg, estimate that in order to reach those Paris Agreement goals, even larger sums of money really have to go to grids, really looking at doubling the global investment from between 600 and 700 billion annually through 2050. So this graph just shows the US investment, which has steadily risen over the past couple of decades, and kind of underpins the importance of investing into this very critical space. Next slide. Getting just a little bit more granular before I turn it over to our experts to dive in deeper. What is grid modernization? What are we aiming to do at the higher level and some of these specific objectives, and how are we aiming to do it? So again, at the highest level, the objective of modernizing your grid is to create a smarter, faster, larger grid that is more flexible and then can integrate these higher shares of renewables. More specifically, what we're aiming to do, focusing today on the integration of variable renewables, but that modernized grid also helps you improve system operations, reducing losses, reducing blackouts, increasing resilience to climate change, lowering costs by creating better enhanced efficiencies across your grid, utilizing existing assets and reducing peak demand issues. Having this bigger modernized grid allows you to better integrate with your neighboring markets, as well as ensuring workforce productivity and safety through things like geotagging your assets and all of those types of things. So the how kind of falls into these three categories. Again, I mentioned there is this critical side of the equation on the regulations, markets, processes, which we won't tackle today, but we will be focusing in on the hardware and the software. So the hardware for energy and communications and data and IT, as well as those software components for data management, planning, analytics, and cybersecurity. These are the things that we're really going to dive into across those country examples today, and hopefully talk a little bit about at the end. So with that, I will turn it over to Alvaro to take us a little bit deeper into the key elements of grid modernization.
Thank you, Amanda, for that introduction. Hello, everyone. This section provides the very basics of grid modernization investment in just 3 minutes and a couple of slides. This is a hugely complex topic, so we are only providing the tip of the iceberg. And we do this because we want to put you in the mental state required to then introduce our framework and compare country experiences. We do so by showing some basic diagrams of what type of investments and systems we are talking about. Next slide, please. In a very simple way, a modern grid has 3 key building blocks. First, intelligent electronic devices that substitute old electromechanical equipment and that allows to remotely visualize and control many parts of the power system. Please see in the slide how we underlined the words remote, visualize, and control. These are the key words of a modern grid. We have also included some metaphors as icons, for example, a remote controller. Second, at the other end, you need a modern control center, which is what you can see at the bottom part of the slide. This is where the people in charge of managing the grid go to work every day. These modern control centers have screens and computers instead of papers and telephones as in the old days. This is where all the data from intelligent electronic devices is received, processed, and instructions are sent back to remote controls. This is done through computer software and processes, and that processes all the information faster and better than humans. Third, of course, you need a two-way communication network that is in between, that sends signals between the intelligent electronic devices and the control centers. Next slide, please. This slide builds on the previous one, explaining how everything is put together for fast and remote metering and control. The left part of the slide is the before and the right part is the after. At the top part, you can see a simplified representation of a power system, from bulk generation on the left to demand on the right. At the bottom is a representation of the control center, before on the left with papers, and after on the right with screens and computers. In the before, on the left side, information to and from the control center flowed through telephones and technicians that had to physically drive to the different places, take measurements with their eyes, and execute control physically, for example, with levers. This took minutes or even longer. The increasing complexity of the 21st century power system and the flexibility required for variable renewables integration require an approach that is faster and less error prone. In a modern grid, on the right side, the control center is automatized and the data gathering and control is all done remotely through communications networks, which is much faster, takes seconds or even less. Next slide, please. This slide goes one step further, showing a modern grid in a very simplified manner. First, look at the three green areas: bulk generation on the left, electricity transmission and distribution at the center top of the slide, and users at the right and bottom. Second, the continuous line, the black continuous lines, show energy flowing through what we have called thick cables, that are cables that actually carry the energy, while the dotted lines show data flowing through what we call thin cables, that are cables only for signals, much thinner. And third, you can see M's for measuring and P's for protection and control. Next slide, please. But modernizing grids is far more complex than what we have explained in the previous slide. Understanding the key components, investments, and actions involved can be difficult. The language can easily get too technical, and there is a clear risk of missing the forest for the trees, creating communication barriers between policymakers, investors, and technical experts, resulting in hurdles to implementation. Therefore, we now present a framework that intends to ease the complexity by visually mapping the types and sequence of investments and actions required. Next slide, please. With our framework, we are trying to move from planning to one step closer to implementation, as Amanda said before. From the more strategic approach that we took in our previous webinar on grid modernization planning in September, today we map specific actions and investments. We do it based on a common framework so that all country examples can be compared. It is similar to existing frameworks being developed in the United States and in Europe, but not widely applied to other regions yet. The framework has some simplifications that allow us to not reach an overly technical level of details for the sake of understanding. We are trying to hit a sweet spot of being 80% accurate. We then apply this framework to 3 real country examples, as Amanda said before, which feature different flexibility needs and stages of grid modernization. The goal is to identify key components across countries while keeping in mind each country's specificity. Ultimately, this mapping could serve as a blueprint on where to start, building understanding, support, and buy-in from policymakers and investors. Next slide, please. Our framework maps investments in 3 dimensions: what, where, and when. A 4th dimension could be why. For example, the driver behind each investment, which could be, as Amanda explained before, for instance, to reduce losses or to improve cost efficiency. Here, we will assume that the why is to unleash flexibility for variable renewable energy integration, even if there are overlaps and synergies with the other drivers. I will now run you through the 3 main dimensions. The what can be either energy hardware, what we call thick cables through which energy flows, hardware for measuring communications, IT, and data, what we call thin cables through which only electronic signals flow, or software, which are bits and code, for example, applications for data management or analysis. The where gives an indication of the location within the power system. For example, if an investment is done on the demand side, on bulk generation, or in control centers. The when addresses the sequence when each investment is required. Yesterday refers to existing assets needing substitution or reinforcement, and that should have been done already. Today means new assets that are the early backbone of a modern grid and that can be tackled today. And tomorrow implies new assets that are the advanced elements of a modern grid and can maybe wait for a bit. But keep in mind that these time steps are just a simplification and may mean different things in different countries. Now, in the country examples you will see, we will display these dimensions in rows and columns, and we will use these tables to map actual investments. We will discuss a few of them, only the most relevant ones for variable renewable energy integration that are marked in blue lines with a solid red background. Now, let me give the floor to my colleague Arai, who will run us through the first country example.
Thank you, Alvaro. So yes, next I will go through the Kazakhstan case, applying the framework that Alvaro just described. Next slide, please. The government of Kazakhstan has held auction rounds each year since 2018. But parallel to the expansion of wind and solar capacity, there has been strong interest in solutions to integrate renewables into the power grid. Key officials understand that growing variable renewable energy will require the system to have dispatchable, flexible capacity. Next slide, please. KIGOC, the national transmission company, has a clear plan for increasing the flexibility of the power grid and generation. Before describing some of the key investments and actions that they're putting in place, there are some policy aspects to highlight. For example, Kazakhstan put in place the Digital Kazakhstan State Program. Digitalization is a key area needed to build flexibility. Digital communications and control equipment allow monitoring of outputs of generation units, as well as the entire power grid, as Alvaro was taking us through. In addition, digitalized systems allow fast dispatch of flexible resources, and if needed, curtailment of generation and load. There are also plans for balancing market, which has operated in test mode in Kazakhstan for several years. However, until the market for trading flexible services comes online, ramping is either uncompensated or rates for ramping are negotiated with flexible generators. And this is actually a very common practice in many of the countries where we work in. New flexible generation is also a part of the solution. Auctions for flexible capacity are being planned, and there may also be purchase of flexible hydro energy from the Kyrgyz Republic. And future renewable auctions are also likely to combine renewable energy with storage facilities. Next slide, please. So in terms of hardware for energy, Kazakhstan has made several investments, and I'll highlight 4 changes to the Kazakh power system, which are a bit darker on the slide so you can follow. So first, automatic generation control has been installed on 5 generating units in the country, and is being installed at a unit in the Kyrgyz hydro complex. Second, central emergency automation was installed to ensure the automatic stability of the power system in the event of a disturbance. Third, new flexible generation resources are being deployed. And finally, energy storage will also be a part of the solution. A test storage facility is planned, and as I mentioned, future renewable energy auctions are likely to combine renewable energy and storage. Next slide, please. I'll highlight communications, data management, and control hardware that are being installed. These are mostly systems that are comprised of multiple pieces of hardware along with software applications. First, hardware for communications and control of generating units, system stability, and distributed resources has been installed and will continue to be augmented. Second, a wide area management is installed and a wide area control system has been recently installed. And to enable all of this, there were upgrades to telecommunication infrastructure, smart meters were deployed, and distribution systems and substations are being automated and digitalized. Next slide, please. Regarding software, a wide range of new applications have been introduced. There's a variety of software used for analysis of the system and the impact of performance of renewables and distributed resources. There's ongoing work on forecasting and modeling of the power system to determine flexibility and integration issues, stability, and safety. Other analytical software include software for the wide area management and the wide area control system, and software for the balancing market, including metering, billing, settlement of transactions, and among others. This is the simplest of our three cases. Next, our esteemed colleague PK Agarwal will describe the India case. Thank you.
Hello, everyone, and thanks, Aray. So I will be presenting the case of India and how this India has gone for grid modernization and flexibility for the RE integration. Next slide, please. This is a brief overview of Indian system. India is the third largest grid as per capacity of the grid, and that is 395 megawatt in 395 gigawatt, and then it is managed by 34 control center. It has presently about 38 point something % of RE integration. The capacity of presently RE is of 153 gigawatt. India is committed to the 50% of total energy through non-fossil fuels as per COPS 26, and for integration of this much large capacity of the renewable energy, India is focused on grid modernization and flexibility in various ways. Next slide, please. So this is some strategies and initiative taken for the grid modernization and grid integration, RE integration in the grid. So one of them is the strategy of upgrading the grid technology, new technologies, upgrading the grid protocols, that is grid code, increasing the balancing area with the cross-border connections, and so that larger balancing area helps in RE integration. And there are some initiative like AGC, REMC, Renewable Energy Control Center, dedicated control centers for renewable energy, introduction of real-time market, dedicated green energy corridors, flexing, giving the compensation to the flexing plants, some of the major initiative taken. And so I will discuss these initiative in the coming slide, which is as per our framework. Next slide, please. So if you see this hardware of for the energy, so there are many initiative has been taken directly or indirectly for the RE integration and providing the flexibility to the Indian grid, but I will only discuss some more important things like 4 or 5. So let us see this one dedicated RE transmission, a dedicated corridor for connecting remote located RE resources to the main grid, national grid. Then second is the advanced sensors. Advanced sensor known as phasor measurement units, which updates data in every 20 milliseconds, unlike 4 to 6 second by SCADA system. So about 1600 PMUs has been installed in India, and all these are making a WAMS, wide area monitoring system, which is very helpful in integration of the variable and unpredictable resources, because it provides the dynamic condition of the grid. Pumped hydro storage is already working in India. About 3 gigawatt of capacity is operational, and it is helping in time shifting of the peak hours, time shifting of the energy from off peak hours to peak hours. And 3 gigawatt of pump hydro is under construction. Then pump hydro is always very difficult to construct and difficult to maintain. So now India is going for the grid level battery storage. And about as per study, about 38 gigawatt of 4 hours capacity is required for integration of 500 plus gigawatt of RE integration in the grid as committed by India for 2030. But presently, India has started putting some pilot project, and recently a pilot project of 500 megawatt with 4-hour capacity has been tendered by the government of India. Next slide, please. So as regard for hardware for data measurements and communication, so India has provided a telecommunication infrastructure wherein every control center and every power plant and every grid grid substation are connected to the fiber optic with the central control center. So this is required for SCADA system, for WAMS, and for having data from sensors. Then substation automation. India started substation automation, implementing digital substations in 2014. That time it was simple digitalization. Now India is going for the advanced version of the digital substation, that is along with the process bus of that. Then distribution automation is also being done in India along with the smart grid. So for managing distributed energy resources, for managing the self-healing, the distribution system, etc. Then National Open Access Registry, a very big application for the existing market is being implemented, which will aid in managing the portfolio of by distribution companies by managing their variability with the open access. Next slide, please. And if you see, the third part of that framework is software. So many software has been implemented for real time, for AGC, for ancillary services, but I will focus on 2 or 3 software which are very important for it. Then one is the software for RE forecasting and aggregation, which has been installed in REMC, which is Renewable Energy Management Center. And this software takes the input from 3 different forecast service provider, and which probably might be on different algorithm or different basis of that. And then it aggregates that forecast and provides some weightage, different weightage to different forecasters based upon its experience of accuracy in the previous days. and then comes out with a schedule. So this is a this is a AI ML based software which has been implemented in 11 control centers in India for REMC. Full-fledged based ancillary services has also been rolled out, and it is being market-based is also being rolled out now. Many softwares, many forecasting software has been developed by Indian utilities for RE and load forecasting, which is being done by different utilities. And as regard to cybersecurity is really important for the software or IT systems. And India has different sectoral certs for the generation, for transmission, for distribution, and especially for operations. So for operation, India has a special CERT, Computer Emergency Response Team, which is dedicated for the system operation in India, and all the grid control centers are part of that, and NLDC is the head for that, managing that. And for the distributed generation resource management, India is also implementing distribution energy management centers. So I think this is from me. I will give floor to Mr. Victor to have the Colombia case study. Thank you.
Thank you, Mr. Agarwal. Good morning, everybody. I would like to provide an overview of Colombia as a case study for grid modernization and how they are facing the different challenges with the penetration of renewable energy sources. So next slide, please. Then let's start with some context on the Colombian power system. Colombia is a country with around 51 million inhabitants. The power system has a peak demand of around 10 gigawatts, and the transmission system is composed by voltage levels between 110 kV and 500 kV. They have one national grid operator and 57 regional operators. The current installed capacity is around 18 gigawatts. And as you can see, the variable rest penetration is very small, with only 1% of the total installed capacity. And the hydro component is very high, with almost 70%. However, it is expected that the installed capacity will be around 27 gigawatts by 2026, and most of the generation expansion is expected in wind and solar projects. Next slide, please. This is the regulatory background. Then I think this is one of the main components to start with the grid modernization in countries. Basically, if regulatory rules are clear, it will be much easier to attract modernization investment. Then Colombia has an electricity market since 1994. They are working in updates for the current grid code according to REST technologies. And they are also working on the transition from passive energy users to active ones. So as a general scheme, Colombia had a reliability remuneration mechanism and bilateral contracts. And now they successfully implement long-term energy auctions to incorporate renewables in their system. The short-term electricity market has a day-ahead market and a secondary reserve market controlled by of course, the AGC. And they are working on an intraday, ancillary, and balancing market. Nodal electricity pricing is also under the scope. They are working on improvements on the grid code, considering large and short-scale rest penetration, energy storage, and distributed energy resources. Regarding active energy users, Colombia has investigated the demand response, energy aggregators, and distributed energy resources but this topic is still pretty new in the system. Next slide, please. Okay, talking about the hardware for energy, as I mentioned before, Colombia has a very high component of hydro generation. Thanks to the number of reservoirs, Colombia has in the hydro technology a very good source of flexibility and support for RES penetration. However, I would like to highlight here some important aspects for the grid modernization and coordination of the power system operation in Colombia. First, in Colombia, it's clear the participation of the generation units in frequency containment reserve, FCR, and frequency restoration reserve, FRR. It made easier the implementation of the automatic generation control. Another important aspect is the ramp up, ramp down characteristics for each generator. These characteristics are certified and declared by each generator to the system operator. The system monitoring is supported by the SCADA system and improved by PMUs. The SCADA has a replacement schedule close to every 10 years, and the last one was in 2018. And they incorporate in this new SCADA system 2 training rooms for operators. The rest of components, such as the fax, battery storage, SVCs, STATCOM, have been implemented for purposes different than the RES penetration, but for sure, those will bring additional support once RES penetration start getting more relevance in the country. The PMUs has been the booster for advanced protection system, and the power system operator is studying the information provided by PMUs to implement intelligent protection system in case of major events. In addition, a dedicated RES transmission system is under construction to interconnect large RES projects to the power system. Next slide, please. For communications, Colombia has all types of communication channels, from optic fiber to mobile, broadband network to satellite, okay? Most of these channels are full use in the power system. And of course, not everything is perfect. Communication also has limitations due to the topography in the country. Colombia has a lot of mountains, but in general, the communication channels are good enough. There's a transition right now from analogic substation to digital substations, and smart meters are moving forward into the system, but their incorporation is going very slowly. Massification of this kind of technology for domestic load is still a challenge. Next slide, please. Regarding the software used in Colombia, they use Power Factory for power system analysis in short, medium, and long term. The SDDP and Plexos are used for energy security analysis. Another very important aspect is they have been developed in-house models to meet particular modeling requirements related to weather phenomena such as El Niño and La Niña. The state estimator is available for the operation of the system, and as data storage for PMUs, they are using Pi. The RE forecasts are being taken very serious. Large RES power plants must provide an RE forecast for every stage of the future intraday market. And the power system operator is also working to obtain its own RE forecast and compare with the one provided with the generators. Cybersecurity is one of the main IT processes, especially for some of the largest system operators in the country. And another relevant aspect is the incursion on carbon markets and providing green certification for clean energy producers. A program called Green Rating to Investors was recently launched in Wall Street to promote investment in green technologies in the country. This is a new step going forward in this big effort to meet the national determined contributions. Well, this was a short overview of some aspects as part of grid modernization in Colombia. I think, Alvaro, I'm back to you.
Yes, thank you very much. Thank you, Arai, PK, and Victor for your country examples. The goal is now to compare countries, identifying key components and common traits. Ultimately, this mapping could serve as a blueprint on where to start. But first, a warning: it has not been easy to find common components because different country experts were using different names for systems that are either the same or work very similarly. For instance, one country expert was referring to FRR reserves, which are secondary reserves provided by automatic generation control, while others were referring to AGC itself, that is the system and not the service provided. This shows the large potential for language barriers in the field of grid modernization investments. Also, it has been a bit hard to divide the investments between hardware for energy, hardware for measurement, communications, IT, and software, because most systems have parts in all three of them. Therefore, in many cases, the difficulties of grid modernization are not only technical, but language related. Once we iterated a few times among ourselves, it became easier to find common ground. And while different systems have different requirements, they are country specificities, we did manage to find some common traits. Next slide, please. Let us recap what investments are found in all countries when it comes to hardware for energy. Key components are grid sensoring and control systems such as SCADA that has been implemented in all three countries, although with some differentiation in terms of scope, the where. These SCADA systems are being substituted or complemented by more advanced measuring systems, such as those based on phasor measurement units, PMUs, that are faster and provide a more accurate picture of the status of the grid. But they also require a more robust, fast, and capable communications network. Another key common investment is automatic generation control providing reserves. It is hardware attached to conventional generators that allow them to provide secondary reserve and contribute in balancing variable generation. Flexible AC transmission systems, FACTS, are other similar technologies are another common denominator. They enable the full use of line capacity while maintaining system stability and providing voltage support. Dedicated RE transmission lines bringing power from areas of high resource potential are also found in all three countries. And the storage is being assessed or planned for different purposes, such as balancing generation and helping in grid management. Next slide. In terms of hardware for measuring communications, data, and IT, a telecommunications backbone is a key component, and it takes many forms. But at the basics, it needs to be fast, have enough capacity, be secure, and be interoperable. Substation automation is also another key component seen across countries, and more countries are also rolling out smart meters that allow for increased demand response at all voltage levels, which is a key feature for future flexibility. Finally, another common trait is wide area monitoring systems for PMUs. Next slide, please. And lastly, in terms of software, things that we have seen very, very clearly as common are demand forecasting software and RE forecasting software. Another key investment seems to be to relate to the standardization of communication protocols. Also, applications for data storage and management are found in all countries. And finally, cybersecurity layers are becoming more prominent, and we see very interestingly the case of India, how they're deploying cybersecurity in the different components of the power system. Next slide, please. Finally, let's draw some conclusions. Countries implement grid modernization for a variety of reasons. The why we discussed earlier. Synergies exist, so countries that started for other reasons can have an advantage when tackling grid modernization for renewable energy integration, such as the case of Colombia. There is no single implementation. No architecture is correct, and it is very country dependent. There are also different paradigms and terminologies. So more effort into this type of mapping and comparison exercises could help in developing best practices and harmonizing terminology. However, we have found some overlaps, which are the following. First, existing bulk generation can provide flexibility without much hardware modifications. Grid modernization measures to tap into it include ramp control, automated generation control and related communications and control systems, and commercial settlement systems, for instance, to meter, account for, and pay for the ramping services provided. Second, remote visibility and control is another key area of investment. Much of what has been implemented globally is based on SCADA systems, but there is a discussion today on whether SCADA can be leapfrogged already. Future systems may require something faster that covers distributed energy resources and that allows for bidirectional energy flows. Next slide, please. Another common investment refers to advanced sensors that allow system operators to gain visibility on grid health and on the impacts of renewable energy generation on power quality. For instance, phasor measurement units, PMUs. Forecasting systems for renewable energy and demand are also key, and they allow to understand the amount and types of flexibility services required. A communications backbone is also fundamental, and it has to be fast, able to handle high volumes of the data, secure and interoperable. Finally, investments in data storage and management and in cybersecurity are also common. All in all, this type of mapping exercises and we have carried out has allowed us to gain some insight into grid modernization actions that could be taken for variable renewable energy integration. Thank you very much. Next slide. And now we go to Q&A.
Alvaro, before you kick off Q&A, I just wanted to take a moment to properly introduce Alan Eisendrath, who is here. He's been answering some of the questions in the chat, and he's here on the panel to help answer a few more questions. He's a senior energy advisor at Tetra Tech. We have pulled him out of his retirement to be with us today and provide some insights. Right now, he's consulting on energy and infrastructure reform, privatization, and finance. By providing strategic guidance, technical assistance, and political and institutional advice. So just letting everybody know that Alan is on board here to answer questions as well, and I'll turn it back to you, Alvaro.
Okay, so we have quite a few questions in the chat. Thank you very much, everyone, for the questions and for attending here. How do we do this? Many of them have been answered in the chat already. I think, first of all, something that is important and Grayson have asked this question, but it's important to underline, policies and markets are required probably earlier than grid modernization investments, and they are certainly the first way or the first thing to look at. So increasing granularity of markets, developing markets for balancing, increasing improving the way policies work, grid codes, these sort of things. However, today the focus of the webinar was mostly on investments for grid modernization, as Amanda explained before. So yeah, that's the first thing that I wanted to explain. What about, maybe PK Agrawal wants to take the question on India that John has asked.
Yes. He's right that the market is required before the investment of flexibility, because if a market is there, then only we will procure the RE generations. And then when RE generation has already been come to the grid, then we require the flexibility. But a study shows that about 20% of penetration in RE penetration in the grid can be handled with the present flexibility. Whatever flexibility is there already existing in the grid can be handled up to 20%. So for procuring that 20% RE, we require market. Did I answer my question? That his question or something else?
Yeah, John, if you feel that your question has not been answered, please type it and we can keep answering. However, I will now shoot a question to Alan, who is here. What are some of the first no regret investments that can be assessed, in your opinion?
Mike, that's a great question. And in fact, that's exactly where we started with this entire webinar. What are some of the first and most important early investments in flexibility? I think what we found in the cases is that automated generation control is one of the first investments. And then, of course, you need the communications and the system operator applications and systems to manage AGC. In addition, no regret investments include some relatively low cost modifications to storage, hydro, and thermal plants. For example, in India, you can they've done some things with thermal plants to increase their flexibility and to decrease the damage that ramping does to the equipment.
Thank you very much, Alan. A question maybe for Amanda here. It's in terms of financing for grid modernization investments.
Thanks, Alvaro. We answered that in the chat a couple of times, so I think we can move on pretty quickly. But just to note that USAID really works on the enabling environment components of all of these spaces, including competitive procurement, de-risking the investments, and general capacity building for our partners in country. But we don't typically directly finance renewables.
Okay.
But Alvaro, there's a great question. I'm just seeing it's not in the chat, but in the specific Q&A component from Grayson Hefner. Grayson, you had several questions. I'm not sure if you want to actually come offline and ask this last one, talking about the economic carrying capacity for VRE. That might be a good one to clarify for folks. Okay, maybe you don't want to come up. Oh.
Here I am. Okay,
okay,
thank you. So yeah, thanks for giving me a second here. So I want to compliment the presenters and Tetra Tech and USAID on this work. It's really interesting and something that is really beneficial to everybody that's working in this field, to see real case studies of how utilities have begun the journey towards a greener grid and more renewable energy. So great stuff. Thank you so much for sharing via this webinar. I just had a quick question on the economic carrying concept. Concept for VRE is something that NREL talked about in some earlier reports. And I'm just wondering, as you invest in more and more grid modernization to get higher and higher levels of VRE, at a certain point, it becomes economically difficult to sustain. did you notice anything about this in the 3 case studies? And are there things about certain systems that would have an economic care result in an economic carrying capacity being higher than at others? So I'm just curious on that point. Thank you.
Maybe Alan, you want to start?
Yeah, I'll make a comment on that. Often people don't realize at the outset that there's a huge amount of flexibility in the existing generation fleet. And so one of the India actually did an absolutely great job of measuring the flexibility of their coal plants, specifically to use it to balance the rapidly increasing RE, and PK could give you more on that. We also, Tetra Tech did testing in Ukraine of the flexibility of the entire generation fleet, and we're beginning the same thing in Kazakhstan now. So that's actually a very cheap and fast source of some flexibility, but it's usually not enough.
Yeah, you are right. In India, flexibility has been got from coal thermal plant without any investment. As mentioned before, also that with the regulation, we could run this power plant, coal thermal power plant by up to 55% of its capacity, which we are running about, not running, going down than 70 to 80% of its capacity. Only what regulators did, that they give some compensation because of the deteriorating heat rate of the plant at the lower minimum level. So India has taken the flexibility from the existing power plants.
I would like to also add here that in Colombia, at the beginning, they also talk if maybe there could be a limit for RES penetration in the country according to the flexibility of the power system. And then one main aspect is always try to assess what's the flexibility capacity that you have in the country in order to know what's the RES penetration that you can afford, or that you are able to manage with your power system.
Victor, now that you're talking, why don't you please also answer the last question that Sarah Lawson asked on how can hydro variability be managed in Colombia with the increasing climate risk on hydropower, El Niño, La Niña, etc.
Hydro generation, thank you so much for this question. And hydro is a very important component for flexibility. Everybody thinks because you can have a very high ramp up, ramp down with hydro generation, you can think that it's very easy and the system is very flexible. But once you start considering all the restrictions, environmental restrictions that you start having for hydro generation, then you just realize that maybe you can start considering the hydro generation as thermal generation for flexibility purposes. Okay, so that's a very interesting topic. And then for the hydro generation, we start considering or including a lot of restrictions related to climate change, related to these weather phenomena, that maybe this is going to decrease the flexibility capacity of this technology for the power systems.
Thank you so much, everybody. We are at time, as always happens. Thank you so much to all of the panelists for sharing, and thank you to everybody who joined and for all of your great questions. I will just quickly say we do have a brief evaluation at the end. It's in the chat box. If you could take 30 seconds to complete that, it helps us do better and get to some more of these questions next time. We have a couple of resources coming out from SURE. The most prominent one is a technical brief on grid modernization that'll be available soon. And you can always go to the SHORE website, usa.gov/energy/SHORE to learn more about any of this work or contact any of us for additional support. So thank you again, everybody, for your time this morning, and we hope to see you soon on another webinar.